So good morning. I'm going to be talking about our work on COTS feeding rates, which is a CSIP-funded project. So as you're all aware, it is the feeding behaviour of Crown-of-Thorns Starfish which make them famously problematic for our reefs. Feeding by COTS is considered to be one of the major and acute threats that undermines reef resilience on the GBR. And as a result of their devastating and costly impacts to coral reefs, COTS have gained major research interest. However, since the 1990s, very little work has been done. This isn't working. There we go. Very little work has been done on the feeding behaviour itself, which has left major knowledge gaps. Having accurate estimations of COTS feeding rates, for example, is essential to understanding their impacts on coral assemblages, and understanding that is essential for effective management of coral reefs. Feeding rate data can also provide us with additional insight into starfish nutritional condition during the course of an outbreak, which is also currently lacking. So with that in mind, we designed a study with the objectives as follows. So firstly, to use advances in technology to establish highly resolved feeding rates, and a key aspect of this would be trying to obtain coral consumption rates at both a 2D and 3D surface area resolution. Secondly, to identify which factors were really driving variation in COTS feeding rates with our large-scale survey design. And lastly, a really important aspect of this study was going to be sharing our new and improved estimates of daily feeding rate with modelers and managers to enable the best possible ecological projections and decision-making. So in order to enable this to be a really large-scale feeding study, which encompassed a huge number of COTS, we used the SALAD survey technique, which is capable of surveying over large distances. And you'll hear a bit more about this technique with Morgan's speech later. But what you need to know is that during surveys, for every starfish that we encountered, we took measurements of the individual itself, and then recorded all of the fresh feeding scars in the vicinity to the starfish, and identified them to genus and also measured them. So for consistency reasons, we considered a fresh scar to be one where the skeleton was lighter than a B2 on a coral watch card, as you can see there. So all scars that we encountered which were darker than a B2 were ignored during surveys. So we previously conducted an exercise where we photographed the aging of COTS scars over 14 days and quantified the point at which scars surpass a hue-based threshold equivalent to that B2. And this was found to be 6 days in the summer months and 10 days in the winter months for a whole series of scars that we did this process for. And this was going to be really important for us later when we were trying to establish daily feeding rates, because we could assume that when we encountered a series of fresh scars on a SALAD survey, all of the scars that we were calling fresh would have been consumed within that time period. So these surveys were conducted over 24 reefs in 5 distinct regions of the GBR, from Townsville in the south to Cape Grenville in the north, over a total of 208 SALAD surveys. A really important aspect of this survey design was that we wanted to be surveying reefs over a whole gradient of latitudes, population density, and coral cover, so that later we could really try to investigate trends in feeding rates. So from these surveys, we were able to collect a huge amount of data on scar measurements. However, as I mentioned at the beginning of the talk, we wanted our feeding data to be a resolution beyond just linear measurements of scars. We saw value in collecting data on 2D planar area of feeding by COTS, and then also the 3D surface area of feeding as well. So photogrammetry presented an opportunity to collect this data. However, it was going to be too time-consuming for us to photogrammetry every single scar that we came across on our SALAD surveys. So what we did instead was we went ahead with the rapid field measurements of scar and colony, and then later used conversion metrics to convert these to 2D planar area and 3D surface area. So unfortunately, there weren't any conversion metrics which were suitable for what we wanted to do at a morphotype-specific level. So we conducted a side project with the University of Sydney, where we modelled the relationship between field measurement of colony and associated surface areas. So what you can see here is an example of one of these models we established for the genus Poecilopora, and this model was constructed from the photogrammetry of 13 Poecilopora colonies, You can see the field measurement on the x-axis and the associated 3D surface area, in this case, on the y-axis. So we completed this process for 15 different morphotypes of corals, and we did that for both 1D to 2D relationships and also 1D to 3D surface area relationships, which involved the photogrammetry of 160 colonies of coral. And we're hoping to publish a paper on this work because we see a whole load of applications of these morphotype-specific conversions, including for things like carbonate budget modeling and things like that. So back to our feeding study. For all of the thousands of measurements of feeding scars that we collected from our surveys, we were now able to use our conversion metrics to convert each of these individual scars to their associated planar area and 3D surface area. So from this, we were able to work out mean daily feeding rates per individual by summing together the feeding data for each individual starfish and then dividing it by the aging factor, which I was speaking about before, which was 6 days for the summer months and 10 days for the winter. So finally, we had our mean daily feeding rates for each individual starfish. So for those of you in the room that work with ecosystem monitoring, modeling, or management, you'll probably be most interested in our data on 2D planar area of feeding rate, because these feeding rates can be related to total coral cover on the reef and will demonstrate the collected damage potential of two ecosystems if COTS are left unmanaged. And for those of you in the room that are perhaps more interested in nutrition and physiology, our data on 3D surface area consumption, which basically signifies total tissue consumption, will be of interest because this data tells us a lot about the underlying explanations for feeding differences between corals and also how these feeding differences may be affecting the physiology of the individuals. So let's have a look at some of our results. So in total, we were able to collect mean daily feeding rates for 540 different individuals, which involved the measurements of over 2,500 feeding scars. So this is by far the biggest COTS feeding study that's been done. We found a lot of variability within our daily feeding rate data set, and so we wanted to try and dig into what was driving that variation. So the most obvious to investigate first was the size of the effect of body size on daily feeding rate, and as expected, we found a significant positive effect of body diameter on daily feeding rate. And with that in mind, we were able to group our COTS into size categories and then calculate mean daily feeding rates for different size categories of COTS. And for ease of use, we've used the same size categories as what is used by the culling teams when they collect their size structure data. So I'll just talk you through what some of these daily feeding rates look like, because sometimes it's hard to sort of visualize that sort of thing. So for COTS in our smallest size category, these individuals were eating around 13 square centimeters on average a day, which is roughly the same size as a small biscuit. Then jumping to COTS in the 25 to 40 centimeter class, these COTS were eating on average roughly around the same size as a CD. And then COTS in our largest size category were eating 241 square centimeters a day, which is roughly equivalent to a frisbee or a small dinner plate. And that's each day. So if we think about that at a reef scale, the collective potential of these large individuals, which we know are making up the majority of our... I'll go back, actually. So we know that a lot of the individuals on our high-density outbreaking reefs at the moment are in the larger size categories, sort of bigger than 40 centimeters. So if we think about the potential for consumption, these large individuals are eating around 6 to 8 square meters of coral per year each. And if we multiply that by the thousands, tens of thousands of COTS that we have on our reefs at the moment, the coral loss potential from these populations is really phenomenal. So now we're just going to have a look at some of the other drivers of feeding rate, and for the figures that will follow, body size has been accounted for to affect that because of the confounding effect. So I'll be presenting relative daily feeding rate. So looking at the role of food availability on daily feeding rate, we found that total coral cover and aquaporin cover were having a weak positive effect on relative feeding rate when total 3D surface area of coral consumed was plotted. However, interestingly, when we considered daily feeding rate to be the number of colonies consumed per day, as opposed to the area consumed per day, there was a negligible or even slightly negative effect of coral cover on daily feeding rate. So you can see those two graphs next to each other. So this is telling us that COTS in low coral cover sites are eating the same number of colonies as COTS in high coral cover sites, however receiving far less surface area and so tissue area per colony that they consume. This is likely because the sorts of corals that dominate high coral cover communities are taxa like Acropora, which are highly complex, and so every colony consumed is offering a large amount of surface area per colony, whereas in low coral cover sites, the dominant taxa are often massive and submassive species, which are morphologically a lot less complex, meaning for the same number of colonies, the actual tissue consumption and nutrient intake would be much lower. We can also infer that for COTS in these two communities to be reaching the same number of colonies, COTS at low coral cover sites are likely foraging a lot further and exerting a lot more effort to receive food. So both of these factors are likely affecting the overall energetic condition of COTS, which will undoubtedly be having an effect on the physiological condition of these populations. So now moving on to the effective region, we did find an effective region. However, this is most likely reflecting the fact that corals around the lizard region are dominated by highly complex corals, which is what I was just talking about. And we didn't find much evidence for an effect of population density or outbreak status on daily feeding rate, at least over the range of densities that we're currently experiencing. So what are the main findings and implications of this study? Our study used a highly accurate photogrammetry method paired with a huge sample size to produce accurate daily feeding rates for over 500 COTS. With this data, we were able to show that COTS feeding rate is influenced by body size and to a lesser degree coral cover. However, population density was not having an effect on feeding rate. This study established mean daily feeding rates for several different size classes, and when these size-specific feeding rates are paired with our data on size structure and population density of known populations, this will enable massively improved estimations of COTS feeding impact for ecological modelling, and in particular will be a key component for refining COTS control thresholds. Additionally, this study has recorded fine-scale data on total tissue consumption by COTS, including taxa-specific consumption rates. This data will be used to better understand the basis of feeding preferences and, moreover, gain an insight into the physiological condition of COTS during the course of an outbreak, which may ultimately explain population breakdown. Our improved understanding and management of this problematic species will provide the best chance for safeguarding the resilience of the reef. Thank you for listening, and thank you for CSIP for funding this research.
Thank you, Josie. That was a great talk. I've got two related questions. Firstly, if I remember that right, Morgan and others had found winter-summer differences quite big in the feeding. And secondly, I'm just curious, are your rates roughly in the same ballpark as the older rates from John Keesing? So we can still say maybe 10 to 15 per hectare is ecologically sustainable?
Yeah, so in response to your first question, yeah, we did also find seasonal differences in feeding rates, but these are most closely tied to the actual spawning, like localized around the spawning time of the year rather than the seasons like just summer and winter. So we found that we had much higher feeding rates in the month of spawning, and that wasn't exactly tied to temperature, for example. So yeah, I thought about including it, but didn't manage to make it into the presentation. And then with relation to Keesing's rates, ours at the moment are a little bit smaller than Keesing's rates. I think they're about 2/3, but we are in the range of what he said was normal. But he had a very small scale study of not very many individuals. So we do, as you can see, we have a whole range, and now we can see that we can pull it out given the size of the individuals and things like that.